Hi, I'm Michael Pfeiffer. This is another episode of the Metal Conversations podcast. In this episode, I'll talk about metallurgical phase diagrams. Now, this is a topic that may strike fear into a lot of you people who took metallurgy in college and were exposed to phase diagrams and were completely overwhelmed with it. It seemed hard to understand, and I'm totally sympathetic to that. When I was in undergraduate metallurgy classes and we were learning the phase diagram, I was also confused. Luckily, I've had many courses on phase diagrams and have had to use them during my career, so I'm at this point very comfortable using them. So phase diagrams are graphical representations of the phases present in an alloy as a function of alloy composition and temperature. And we use phase diagrams to help understand the phases that are present in an alloy after the alloy has been exposed to some sort of thermal cycle or thermal treatment. It could be solidification or a heat treatment or welding, brazing, or soldering. And we want to understand the effects of the alloy composition and heat treatment or thermal cycling on the phases that form, because the phases that form influence the properties of the metal. So first of all, I want to define what a phase is. So a phase is a physically distinct material. And with metals, this means that a phase is defined by the composition of the phase, that is the element or elements present in the phase. It's also defined by its crystal structure, that is the arrangement of atoms in that phase. And it's also defined by whether the phase is a mixture or a compound. A mixture means that it's one element, it's the main element that's arranged in a periodic manner, and then alloying elements that are mixed in randomly throughout. So for example, in steel, an example of a steel phase is ferrite. And in ferrite, the ferrite is be a mixture, and it can have other atoms mixed in with the iron atoms in the ferrite. Those other atoms might be carbon or manganese or nickel atoms, other alloying elements that are mixed in. And sometimes phases are a compound, where it's a specific ratio of one element to another. So it's almost kind of like a reaction between the different elements. And an example in steels, again, is iron carbide, where there are 3 iron atoms for every carbon atom. So a phase diagram indicates the phase or phases that are present at any particular temperature and alloy composition. Now, there are what's called binary phase diagrams, and then there are tertiary and quaternary phase diagrams and more complicated phase diagrams. So the simplest type of phase diagram is the binary phase diagram. Binary phase diagram represents the phases that are present based on the temperature and two elements present in an alloy. If it's steel, we're concerned with the iron-carbon phase diagram. The diagram shows iron and then different amounts of carbon, increasing amounts of carbon in the iron. Another example would be the aluminum-copper phase diagram, where the phase diagram shows aluminum at the left end of the axis, 100% aluminum, and then increasing amounts of copper as we move from left to right along on the phase diagram. That phase diagram shows the phases that form in the aluminum copper alloys for different amounts of copper present in the aluminum and at different temperatures. And in the iron carbon system, the phase diagram shows the different phases that are present in iron alloys and iron and carbon alloys, depending on the amount of carbon present in the iron. Now, most phase diagrams show 100% of one particular element on one end of the axis, of the x-axis, and 100% of the other element of consideration on the other end of the x-axis, and then increasing amounts of that second element as we go from left to right. There are different regions within the phase diagram that indicate the phase or phases that are present based on the composition of the alloy and its temperature. For example, in steel, if we have a steel that has 0.5% carbon in it and it's held at 1,000 degrees Celsius, then we can look at the phase diagram and determine that steel then at that temperature will consist of austenite. And then if we look at that same phase diagram and we say, well, what will happen when we cool the steel? And we can look at the phase diagram and understand the phases that form as the steel cools, because as we pass through different regions on the phase diagram, we can identify the different phases that form during cooling. This helps us understand the effects of heat treating. Also, this could be used during solidification for casting, for steel casting, or also for cast iron casting. We're trying to understand the phases that form during the cooling of the cast iron metal. During processes like welding two pieces of metal together or brazing or soldering, then we're concerned about the solidification of the weld metal. For brazing and soldering, we're concerned about the reaction between the molten braze or solder material and the metal to which it's joining. And we can use phase diagrams to understand and predict the reactions that will occur. Now, the phase diagrams that we use, that I've talked about, the iron-carbon phase diagrams and the aluminum-copper phase diagram, those are binary phase diagrams, and they show the phases that form for different compositions of iron and carbon or aluminum and copper. When more alloying elements are added to the metal, then that will change the phase diagram. So we'll talk about the iron-carbon phase diagram. As steels contain iron, carbon, and other alloying elements, so carbon steels contain iron, carbon, manganese, a little bit of silicon, or maybe a little bit of aluminum. Sometimes they contain copper. And those additional alloying elements will alter the phase diagram, change the shape of the different regions where they indicate the different phases, also change their locations, may move them up and down or from left to right. And then for steels like low alloy steels that also contain nickel or molybdenum or chromium, those elements also alter the phase diagram. However, understanding the basics of the iron-carbon phase diagram is very helpful for understanding the changes that occur during heat treating of steel, and we can apply the iron-carbon phase diagram to these other steels that have additional alloying elements. For steels that have more alloying elements than just carbon, we can refer to handbooks that contain information about the temperatures to use for heat treating, because we can't rely on the temperatures that are shown on the iron-carbon phase diagram, because those temperatures don't apply to steels that contain additional alloying elements beyond carbon. But understanding the iron-carbon phase diagram is still very helpful for understanding the effects of various heat treatments on steel phases and microstructure. Overall, just to kind of give the 1,000-foot view, understanding the phases that form is important, because the phases that form are a critical factor in influencing the properties of a metal, whether it's a steel or aluminum copper alloy or any other, or a titanium alloy or any other alloy. Being able to predict the effects of heat treating and composition on the phases that form is important for being able to understand what the phases that will form for a particular alloy and heat treatment, and the effect, and then understanding the effects of the phases that form on the properties of a metal. The goal is to form metals that have specific properties for a particular application. So the phase diagrams are very helpful for understanding and being able to predict what happens, and they're also helping for understanding what might have happened to a metal when there's a problem and there's something wrong with its microstructure, something wrong with the phases that are present. And we can look at the phase diagram and try to understand what might have happened to the metal, what might have happened during the heat treatment or solidification or welding that caused the phases to form that were not desirable. So it is not a theoretical or academic tool, it is a practicing engineering tool. So that's it. For people who are involved in engineering and who do understand that being able to engineer metals and understand the science of metals is important for being able to engineer products, then hopefully you'll enjoy this. One more thing, there's a new blog post on the Industrial Metallurgist website on phase diagrams. It's called Alloy Phase Diagrams. So it has the pictures that I'm referring to, the phase diagrams I was referring to, so for help. And also I just made a video that's on YouTube. It's called Phase Diagrams. It's on the Industrial Metallurgist channel, and you can watch that if you're interested in learning more about phase diagrams and seeing the actual phase diagrams in a discussion with the phase diagram in front of you. So that's it. Thanks for listening, and I hope you enjoyed this podcast, found it to be informative, if not interesting, and good luck with your metals. Bye.